Hello there, and welcome to this soft, quiet space beneath the blanket of night. I'm so happy you've chosen to drift here with me. Allow the stillness to settle around you, like fine dust in a peaceful room. Let your thoughts slow down, like the shadow of the moon moving gently across the landscape. Tonight, we'll turn our gaze far beyond the familiar, to the edges of our solar system, a place colder and darker than we can imagine. Out there, in the deep celestial freezer, things are stirring. We're going to whisper about these ancient, icy travelers, the comets, which are making long, dramatic journeys toward the sun. These visitors from the deepest dark are showing us a portrait of our solar neighborhood that's much older and far more complex than the one we learned about in school. We'll follow their luminous tales and listen to the secrets they carry about the very beginning of our cosmic home. If this gentle journey into the darkness helps your mind unwind and brings you a measure of calm, please consider a soft like and a quiet subscribe. It's the gentlest way to help others find their way to this restful, unhurried space. There's no need to rush. When you're ready, we'll begin this warm exploration together. In July of 1994, a different kind of light show was unfolding far away, on a world we usually see only as a bright banded disk in the sky. Telescopes on mountaintops, antennas in quiet deserts, and spacecraft drifting between the planets all turned their attention toward Jupiter. Scientists knew that something rare was about to happen there, something so powerful that it would briefly rewrite part of the giant planet's face. A broken comet named Shoemaker-Levy 9 was on its final approach. For most of its long, cold life, this comet had been just another small traveler in the dark. Like many comets, it had spent ages far from the sun, its ices frozen hard, its surface untouched except by starlight and the occasional tiny collision. But at some point, its path had carried it too close to Jupiter, the largest of the 8 planets. Jupiter's gravity is immense, like a deep well in the fabric of space, and instead of letting the comet pass by, it caught it. Astronomers call this a captured object, something that once orbited the sun on its own, but was tugged into a new dance around a planet. Jupiter has done this many times. Some of its small, irregular moons are almost certainly old asteroids and comets that wandered too near and never quite escaped again. Shoemaker-Levy 9 became one of these prisoners, turning not around the sun directly, but around Jupiter on a long, stretched-out path. When Carolyn and Eugene Shoemaker and David Levy spotted it in 1993, using a telescope at Palomar Observatory in California, they weren't seeing sweeping tails and glittering ice. They were seeing faint smudges on photographic plates, tiny marks in silver grains, but they recognized the shape of the story. This was a periodic comet, one whose journey around its new center would take less than 2 centuries, a traveler that returns instead of vanishing into the dark forever. And almost at once, they could tell that this comet was strange. First, it was large. The biggest pieces were around 2 kilometers wide, comparable to a small city made of rock and ice. Events involving impacts of that scale are thought to be incredibly rare, something like a 1 in several thousand-year occurrence for a planet like Jupiter. Second, the comet was not whole. In the images, it appeared not as a single point, but as a chain of them, like a string of dim pearls. At some earlier time, on a closer pass by Jupiter, the tidal forces, the difference between the strong pull on the side facing the planet and the weaker pull on the far side, had torn it apart. Instead of one solid nucleus, there were many fragments following one another along the same path. Most striking of all was the shape of that path. Orbits can be nearly circular or very stretched. Astronomers measure this with a number called eccentricity. 0 for a perfect circle, values closer to 1 for a more elongated ellipse. Shoemaker-Levy 9's orbit had an eccentricity of more than 0.998, so high that, drawn to scale, it would hardly look like a loop at all. It was as if the comet were rushing in along a nearly straight line, curving just enough to be turned back, then racing out again toward the dark. When they calculated the details of that motion, astronomers felt a quiet shiver of recognition. The path did not only come close to Jupiter, it crossed the planet itself. At first, there was uncertainty, room for the possibility that the comet would skim past or miss entirely. But as observations accumulated and the measurements grew more precise, the numbers began to line up in a steady, insistent way. The fragments were on a collision course. Barring some unknown surprise, they would not just pass by Jupiter, they would hit it. Somewhere in that realization, the event stopped being just an interesting object in the sky and became something else, a rare chance to watch in real time what usually only leaves fossils and scars. Our solar system is full of evidence of earlier impacts, craters on the moon, battered surfaces on Mercury and Mars, structures in the outer planets' atmospheres, and, here on Earth, buried basins and a layer of rock linked to the asteroid, thought to have ended the age of the non-avian dinosaurs. But almost always, we arrive late. We see the wound, not the blow. With Shoemaker-Levy 9 and Jupiter, we would be on time. As the calculations settled, one date rose out of the equations: July 1994. For months leading up to it, observatories around the world watched as the chain of comet fragments crept closer, each one given a letter: fragment A, fragment B, fragment C, and so on. The comet itself remained a faint, modest thing in the eyepieces, but everyone understood what was coming. Each fragment carried the energy of millions of nuclear weapons. Together, they would turn a small part of Jupiter's atmosphere into a temporary storm of unimaginable violence. And still, from where you or I might stand under the night sky, none of that drama was visible. Jupiter remained just a bright point or a tiny disk. The true fever of anticipation lived in control rooms and observatories, in the minds of people who had spent years thinking about gravity and ice and orbital mechanics. The waiting turned out to hold a small sting. Shoemaker-Levy 9's path around Jupiter meant that when the first fragment finally struck, the impact point would be on the far side of the planet, the hemisphere turned away from Earth. The blast would happen out of sight. For a moment, it seemed as if the most dramatic instant of the whole event would be hidden behind Jupiter's broad curve, like a lightning strike on the far side of a distant storm cloud. But our eyes were not only on Earth. Far from home, a spacecraft named Galileo was falling slowly toward Jupiter on a long, looping trajectory. Launched in 1989, it had been traveling for years, adjusting its path with flybys of Venus and Earth, gathering speed, step by gentle step. In July 1994, it was about a year away from finally entering orbit around Jupiter. By pure good fortune, its position in space gave it a clear view of the side of Jupiter we could not see from here. When the time came, Galileo turned its instruments toward the region where the first fragment, A, was predicted to hit. Elsewhere in the solar system, other spacecraft also paused their main tasks for a while. Ulysses, which had been sent to study the sun's polar regions, pointed its detectors toward Jupiter. Voyager 2, far out beyond Neptune, adjusted its radio and ultraviolet instruments to listen for any changes. It was as if a scattered family of robotic observers, each on its own journey, had all agreed to look in the same direction for a moment. On July 16, Fragment A struck. From Earth, the first sign came not as a bright flash to the eye, but as data. From Galileo's vantage point, though, the collision unfolded against the curve of Jupiter's limb. A sudden flare bloomed, where a moment before there had been only the smooth gradient of cloud tops. A towering fireball rose, heating the surrounding gases to temperatures of tens of thousands of degrees, far hotter than the visible surface of the Sunday. The plume shot up thousands of kilometers above the top of Jupiter's clouds, so high that if it had been laid flat along Earth, it would have stretched from one edge of Australia to the other. No one had really been sure they would see such a fireball. Some models had suggested that the impact might be swallowed almost entirely beneath the top layers of the atmosphere, hidden from view. Instead, the comet fragment dug deep, then exploded, sending material back up and out in a great arc. For a brief moment, an invisible piece of ice and rock that had wandered in darkness for billions of years announced itself with a glow that instruments could barely contain. And then, gravity did what gravity always does. The plume reached its peak and began to fall back. Chunks of heated, chemically altered debris plunged into the atmosphere again, compressing and heating the gas in front of them, sparking secondary flashes as they burned and dissolved. The region around the impact point became a furnace of complex motion, rising and falling currents, shock waves spiraling outward, gases mixed and churned on scales larger than continents. Jupiter's day is short, only about 10 hours long. The giant planet spins quickly, carrying its bands and storms, and now its fresh wounds around and around. Within a short time after the first impact, the rotation brought the affected region into view from Earth. Telescopes waiting in the dark suddenly had something to see. Where the comet fragment had struck, a dark bruise now marked the cloud tops, darker and, for a while, more visually striking than Jupiter's famous Great Red Spot. Through the eyepieces and on the screens, that bruise looked almost like a fingerprint pressed into the planet's upper atmosphere. Around it, subtle ripples extended outward, shock waves moving through the dense layers of gas at speeds of hundreds of meters per second. And that was only the beginning. Shoemaker Levy 9 had not one fragment, but many. Over the next 6 days, from July 16 to July 22, piece after piece plunged into Jupiter, each impact carving its own temporary mark. Some were smaller, leaving modest dark spots and ripples. Others were enormous. On July 18, Fragment G, one of the largest in the chain, arrived. When it hit, the energy released was estimated to be hundreds of times greater than that contained in all the nuclear weapons on Earth combined, on the order of hundreds of millions of standard atomic bombs. Again, a great fireball rose. Again, a plume pierced the skies of Jupiter, then fell back in glowing fragments. When the rotation turned that sight toward us, the resulting scar was about as wide as Earth itself, a darkness 1 planet diameter across, painted onto the swirling creams and ochres of Jupiter's bands. For months afterward, even modest telescopes could pick out those marks, reminders of the brief storm of impacts that had battered the giant planet's face. From a distance, in the quiet of a nighttime backyard, it might have been hard to imagine the scale of what had happened. Jupiter still looked the same to the unaided eye, steady, bright, indifferent. But for those watching more closely, and for the instruments recording each flicker and change, Shoemaker Levy 9 transformed Jupiter from a distant, unchanging ornament into a living, vulnerable world, one that could be struck and scarred. It also gave us something rarer still, a glimpse into how planets, including our own, carry the memory of ancient collisions. The Earth bears its own scars from past impacts, though many have been softened by oceans, weather, and the slow drift of continents. One of those old blows is thought to have played a role in ending the long reign of the dinosaurs and reshaping the history of life. Those events are separated from us by tens of millions of years. Shoemaker, Levy 9, and Jupiter offered a quieter kind of intimacy, the chance, just once, to watch such a story being written instead of only reading its traces. As you picture those fragments falling one after another, you don't have to hold every number in your mind. It is enough to remember that for a few days in 1994, the largest planet in our solar system became a kind of slow, silent fireworks display in wavelengths our eyes cannot see. A chain of icy cities, each no wider than a few kilometers, met a world big enough to hold more than 1,000 Earths and left marks large enough for small telescopes to find. The universe was reminding us, gently but firmly, that even the biggest worlds are still part of a shared, restless dance, where orbits cross, paths intersect, and from time to time, something from the deep dark comes rushing in and leaves a bruise that takes a while to fade. And then, when the last fragments of Shoemaker Levy 9 had finished their violent fall into Jupiter, it would have been easy to think the story was over. The fireballs had risen and faded. The bright flares in Galileo's instruments had quieted. The chain of icy bodies had spent itself. But for the scientists watching, the days and weeks after, the impacts were just as precious as the moments of collision. The bruises left behind became windows. Jupiter has always kept most of its secrets hidden under thick, swirling clouds. Usually, all we can study are the very top layers of its atmosphere, the bands of cream and rust, the pale ovals and stormy spots. The deeper regions stay out of sight, wrapped in haze. Shoemaker Levy 9 changed that, just for a little while. Each impact punched deep into the planet's atmosphere and then sent material surging upward, like bubbles rising through a dark ocean. Hot plumes shot far above the usual cloud tops, carrying with them a mixture of the comet's own substance and gases from deeper inside Jupiter. When those plumes spread out and cooled, they left behind dark patches and arcs. To the eye, they looked like smudges and stains. To instruments tuned to split light into color, they were rich with information. By passing the light from those scars through spectrographs, scientists could read the chemical fingerprints hidden in it. Every molecule leaves its own pattern of lines in a spectrum, a quiet signature of its presence. In the aftermath of the comet, Jupiter's atmosphere began to speak a little more clearly. Within those signatures, astronomers found traces of diatomic sulfur, simple molecules made of 2 sulfur atoms. They detected carbon disulfide and hints of heavier elements such as silicon, iron, and magnesium materials we usually associate with rock, not gas. These likely came from the comet's solid core, broken up and vaporized. but stirred into Jupiter's own air and lifted high enough for us to see. Most intriguing of all was the evidence for water. No one was sure what to expect on that front. Jupiter is mostly hydrogen and helium, and although water is thought to be an important part of its deeper layers, it doesn't simply float in plain view above the clouds. Yet the spectra taken after the impact suggested significant amounts of water-related molecules in the impact regions. It was as though the comet had briefly dipped a cup into Jupiter's hidden depths and splashed some of that material upward, letting us glimpse it before it sank and mixed again. Some of that water surely came from the comet itself, whose ices were full of volatiles. Some may have been drawn from Jupiter's deeper atmosphere. Either way, it sharpened a question that would become central for future missions. How much water does Jupiter really hide, and where? Years later, NASA's Juno spacecraft would be sent to orbit Jupiter, with one of its main goals being to map that water, how it is distributed, how much there is, what it can tell us about the planet's birth. Shoemaker-Levy 9 could be seen as a rough, explosive preview of that work, a natural experiment, forcing open a small hatch before Juno arrived to explore more gently and methodically. The comet's legacy, though, was not limited to chemistry. It also reached into something softer and more human, our sense of how safe and stable the solar system around us really is. For a long time, the common picture of our cosmic neighborhood had a comforting frame. The early solar system was imagined as a chaotic place, newborn planets colliding, moons forming from giant impacts, leftover debris racing around on unstable orbits, striking worlds much more often than they do today. Over billions of years, that debris was thought to have thinned. The biggest, most dangerous objects either merged with planets, were tossed far away, or fell into the sunday. The era of frequent, catastrophic collisions seemed to belong to a distant past. Watching Shoemaker-Levy 9 slam into Jupiter added a new layer to that story. Yes, things are calmer now than they once were, but calmer does not mean still. Here, in the late 20th century, while people on Earth were going to work, reading the news, and quietly living their lives, a chain of icy bodies larger than cities was falling into a giant planet with the energy of hundreds of millions of nuclear bombs. It raised a gentle but unsettling question. Was this a once-in-many-millennia stroke of luck that we happened to see? Or are such impacts less rare than we assumed, only hard to catch? Our best telescopes and detectors have existed for less than a century or so, a tiny blink of time in planetary history. For most of Earth's existence, events like this would have played out unnoticed by any eye or camera. And of course, another question came soon after, this time closer to home. If an object the size of the largest Shoemaker-Levy 9 fragments were to hit Earth instead of Jupiter, it would not simply make interesting spots in the sky. It would be an extinction-level event for most complex life. The asteroid, believed to have ended the age of the dinosaurs, was probably comparable in scale. That thought pressed in on people's minds. It showed up in documentaries, in articles, even in movies. The idea of planetary defense moved from science fiction into the vocabulary of real space agencies and governments. Before the comet's impact, few official programs were dedicated to systematically watching the sky for large, potentially dangerous objects. Afterward, it became harder to argue that we could afford not to look. NASA and other organizations began to put more focused effort into finding and tracking what they called near-Earth objects, asteroids, and comets. whose orbits bring them close to our planet. One early goal was to discover and catalog most of the asteroids larger than about 1 kilometer across in Earth's neighborhood, since objects that big are the ones most likely to cause truly global damage. Reaching that goal meant long, quiet work. Telescopes, scanning the sky night after night, taking images of the same regions, then comparing them to find tiny points of light that had shifted slightly. Each moving speck was a small world, an object orbiting the sunday. Over the years, thousands of such bodies were identified, measured, and their paths projected into the future. Today, most of the kilometer-sized near-Earth asteroids we might worry about have been found. The focus has shifted to smaller ones, down to roughly 140 meters wide, too small to end all life, but large enough to devastate a region the size of a large city or country. Hearing about all this can make the night sky feel a little more crowded, but it's important to remember that the danger did not suddenly appear. What changed after Shoemaker-Levy 9 was our willingness to see it clearly and to prepare. The rocks and icy bodies were always there. Now we simply know more of their names, and we watch them with a steadier gaze. Amid these concerns, there is a quieter, comforting thread woven through the story: the role of Jupiter itself. Jupiter's mass is immense. Its gravity is like a deep hollow in the fabric of space-time, reaching far out into the outer solar system. Comets and asteroids that wander through that region feel its pull. Some are nudged into slightly different orbits. Some are thrown outward. Some inward. Some are captured into looping paths around the giant planet. And some, like Shoemaker-Levy 9, end their journeys by colliding with it and vanishing into its clouds. We know that Jupiter is struck far more often than Earth is, perhaps thousands of times more frequently when it comes to certain classes of comets. From one angle, that makes Jupiter seem like a battered guardian, always under fire. From another, it suggests a kind of shield. Every icy or rocky body that Jupiter captures or absorbs is one that will never come sliding silently into the inner solar system to cross Earth's orbit. This idea that Jupiter helps protect Earth by sweeping up or deflecting debris has become one piece of a broader conversation about how special our planet might be. According to the so-called rare Earth hypothesis, complex life, like the kind we see here, may depend on a delicate combination of conditions: the right kind of star, a stable orbit, liquid water, a protective magnetic field, a large moon to steady the planet's tilt, active geology, and perhaps a giant outer planet to take many of the worst hits. In that view, Earth is not just lucky, it is balanced on a narrow ledge of favorable circumstances, and Jupiter's presence is part of that balance. Without a massive neighbor acting, at least some of the time, as a cosmic vacuum cleaner, the inner solar system might have seen more frequent extinction-level impacts, repeatedly wiping the slate clean before complex life had a chance to flourish. Not everyone agrees on how strong this protective effect really is. Some models suggest that a giant planet like Jupiter can also disturb the orbits of distant objects in ways that occasionally send them inward, potentially increasing the flux of smaller bodies into the inner regions. The reality is probably a mix of shielding and stirring. We are still working out how that balance looks over billions of years. What is certain is that Shoemaker-Levy 9 pushed us to ask these questions more carefully. It reminded us that the solar system is dynamic, not frozen, that planets, comets, and asteroids are still interacting, and that our own story here on Earth is intertwined with the quiet traffic of bodies moving through space. For all the concern it stirred, the event was also undeniably beautiful. The dark scars on Jupiter slowly stretched and smeared as high winds tugged at them. Over weeks and months, the marks faded until they blended back into the background patterns of clouds. To most casual observers, Jupiter eventually looked as it always had. But for those who had watched closely, the planet was changed, not in shape, but in meaning. It had become a place where we had seen a profound kind of violence and learned from it. If you zoom your imagination outward, just past Jupiter's orbit, another curious player waits in the dark. While Shoemaker Levy 9 gave us one intense burst of drama and then was gone, there exists a comet that has been misbehaving for years. It doesn't fling itself against a planet in one final act. Instead, it flares again and again, far from the sun, in a region where most things remain cold and quiet. Rather than saving its energy for a close pass by the sun, it seems to erupt on its own schedule. This is Comet 29P, an icy body many astronomers now consider among the most active comets known. Most comets grow brighter slowly as they approach the sun, their ice is warming and turning to gas, forming hazy comae and long, graceful tails. 29P behaves differently. It can become hundreds of times brighter within just a few hours. At times, it has erupted several times in the span of a couple of days, each outburst sending fresh plumes of material out into space. These are not gentle sighs of vapor. During its strongest episodes, 29P can eject more than 1 million tons of dust and gas, rushing outward at speeds faster than the speed of sound in Earth's atmosphere. To observers on Earth, this shows up as sudden jumps in brightness, a faint point of light swelling unexpectedly, then slowly fading back down. What makes this behavior especially puzzling is the comet's orbit. Unlike many comets that dive inward toward the sun on long stretched paths, 29P moves on a nearly circular orbit out between Jupiter and Neptune. It does not swoop close to the sun and then retreat. It lingers in the outer solar system, where sunlight is weak and still manages to be explosively active. There is no obvious trigger like a sudden warming to explain its fits. Astronomers have been watching 29P for nearly a century, trying to understand what lies beneath its erratic mood. It was first noticed in 1927 at the Hamburg Observatory in Germany. Two astronomers, Arnold Schwarzmann and Arno Arthur Wachmann, were comparing photographic plates of the night sky, carefully examining the same star fields taken on different nights, looking for anything that moved. On one set of plates, they found a small shifting point, an object traveling slowly against the fixed background of stars. At first, the new object was classified as a short-period comet, one that would return on timescales shorter than 2 centuries. As its orbit was refined, astronomers realized it lived in that broad middle region between Jupiter and Neptune. That placed it among a group of bodies now known as centaurs. Centaurs are strange, in-between objects. Some resemble asteroids, dark, rocky, apparently inert. Others show comet-like behavior, outgassing, forming comae, and short tails. Their orbits are often unstable over very long times, shaped by the constant gravitational influence of the giant planets they wander among. The name suits them. Just as mythical centaurs are part human, part horse, these celestial centaurs are part comet, part asteroid, refusing to belong entirely to either group. Many centaurs, including 29P, are thought to have started their lives even farther from the sun, in the Kuiper Belt, a wide ring of icy bodies beyond Neptune. Over the last few million years, subtle, repeated tugs from the giant planets have nudged some of those objects inward. Little by little, their paths have shifted until they now roam between Jupiter and Neptune instead of beyond them. So 29P is likely a migrant from the deep cold, now living in a somewhat less distant, but still chilly, orbit. And yet, in that dim region, it behaves as if it carries a restlessness inside it. Maybe hidden pockets of gas beneath its surface suddenly break through. Maybe layers of different ices interact in complex ways, with certain temperatures triggering abrupt changes. Maybe there are fractures and caverns that collapse from time to time, exposing fresh material to sunlight. The truth is that, for now, much of its behavior remains mysterious. Modern observatories keep returning to 29P, waiting to catch the next outburst in as much detail as possible. They watch how its coma changes, how quickly its brightness climbs and falls, how the shape of the surrounding cloud of dust evolves. New instruments, like the James Webb Space Telescope, are beginning to add their own sensitive measurements, offering clues about what 29P is made of and how its surface might be arranged. Where Shoemaker Levy 9 taught us about the power of impacts and the way a planet like Jupiter responds, 29P invites us to wonder about what can make a small world so restless, even in the cold. Both stories, in their own ways, remind us that the solar system around us is not finished or frozen. It is still breathing, still changing, still capable of surprises. As you rest and imagine these distant scenes, the scars on Jupiter fading, the strange little comet flaring in the dark you are sharing, in a very quiet way, in that ongoing motion. The same sky that arches over you holds all of this: bruised cloud tops, wandering ice, sudden bursts of light. And even from here, far away, you are allowed to listen and to follow that motion a little farther outward. Out in the region between Jupiter and Neptune, centaurs live unsettled lives. Their orbits are usually stretched and unstable, not the calm, neat paths you might imagine from a drawing of the solar system. Over time, the slow, steady tugs of the giant planets disturb them. Many of these small bodies will eventually be flung inward toward the sun, becoming active comets that sweep through the inner solar system. Others will be tossed outward, sent drifting into the deep dark beyond the planets, perhaps never to return. In that sense, centaurs are in-between things, not only in their nature, but in their fate. They are thought to be way stations in a journey that begins in the distant Kuiper Belt, a wide, cold ring beyond Neptune, and ends either as a Jupiter family comet visiting the inner solar system, or as a small body ejected entirely from the sun's grasp. Their time as centaurs is brief on cosmic scales, a transitional stage in a long, wandering life. Centaur 29P is one of these travelers, and its story may be about to change again. Calculations suggest that as soon as the 2030 seconds, perhaps around 2038, a close alignment with Jupiter could nudge it onto a new orbit. A conjunction like that is a kind of quiet encounter. Jupiter passes not far away, and its strong gravity gives the centaur a small but crucial push. That gentle shove can reshape the path of 29P's journey, sending it inward to join the family of comets that loop closer to the sun, or outward into a different, more distant track. But even before that happens, 29P already stands apart from most of its cousins. Where many centaurs move on elongated elliptical orbits, 29P traces an almost perfect circle around the Sunday. If you were to draw its path, it would look more like a smooth ring than a stretched oval. That is unusual out there, among objects whose histories are full of gravitational jolts and slow, irregular migrations. It is also big. With a diameter of about 60 kilometers, 29P is wider than the vast majority of centaurs, larger than more than 90% of them. Among all known cometary bodies, it ranks among the giants. If you could place it gently on Earth, it would cover an area comparable to a small country, a cold, rounded world of its own. And then there is its most dramatic habit. It explodes a lot. In terms of activity, only one body in the solar system seems to outdo it: Io, Jupiter's violently volcanic moon. 29P is considered the second most active object we know, erupting on average about 30 times each year. Some of those outbursts are modest, but many are not. Close to half of its stronger eruptions refuse to follow any clear schedule. They come without warning, sudden and intense, like a quiet hillside that, for reasons you cannot see, occasionally rips open and exhales. When 29P flares, its brightness climbs quickly. After an outburst begins, the comet can reach peak brightness in just 2 or 3 hours. In 2024, it drew attention around the world when it erupted 4 times in only 48 hours. For a little while, it appeared nearly 300 times brighter than its usual state, turning from a faint, overlooked point into a noticeable presence in the telescopes of anyone who happened to be watching. 2 years earlier, it had shown a similarly dramatic mood. During one outburst, 29P hurled more than 1 million tons of dust and gas into space, an amount of material hard to picture, streaming out faster than the speed of sound in Earth's atmosphere. It was like an impossibly overpressurized champagne bottle finally losing its cork, except the bottle was an icy world and the spray was frozen debris. That main event did not stand alone either. 5 and 7 days later, smaller secondary eruptions followed, echoing the first blast. That pattern, a large outburst followed by weaker ones a few days later, seems to be part of 29P's personality. And even those wild episodes were not the comet's peak performance. In September 2021, 29P underwent the largest outburst seen from it in about 40 years. It erupted 5 times in quick succession, piling blast upon blast. For a while, its coma, the hazy cloud of gas and dust surrounding its nucleus, swelled and brightened dramatically. Strangely, it was not a big research observatory that first noticed what was happening. It was a collection of amateur astronomers. This is one of the charming quirks of 29P's story. Many of its eruptions, including some of the most impressive, have been spotted first by people with backyard telescopes and a love of the night sky. Professional instruments are powerful and precise, but they are also busy and heavily scheduled. Time on a large, publicly funded telescope is precious, carefully allocated months in advance. By contrast, a dedicated observer with a modest telescope can drift outside on a clear night, point their instrument at a favorite patch of sky, and simply look. When some of these hobbyist stargazers noticed that 29P had suddenly brightened in 2021, word spread quickly. Professional astronomers, alerted by the reports, rushed to request observing time on larger telescopes. They even managed to secure a slot on the Hubble Space Telescope, a rare chance to examine the outburst in great detail. For a moment, it looked as though we would be able to see this exceptional event with one of our sharpest eyes in space. But the universe is not always cooperative. The day before Hubble was scheduled to turn toward 29P, the telescope experienced a technical glitch, a kind of electronic stumble that took its instruments out of action temporarily. By the time the problem was fixed and Hubble was ready to observe again, the most intense phase of the comet's outburst had passed. Once more, 29P kept some of its secrets just out of reach. To understand what drives these eruptions, scientists have had to piece together clues from many such episodes. One of the key ideas that emerged is that 29P is not just any comet. It is what we call cryovolcanic. The word volcano usually brings to mind red-hot lava, glowing fountains of molten rock, and black smoke rising into the air. A cryovolcano is the same kind of process played at a much colder temperature. Instead of melted rock, the magma is made of icy slurries and volatile gases. The landscape is frozen, but it is not inert. Beneath the surface, something is still moving. In the case of 29P, the nucleus is thought to be wrapped in an icy crust, a hard shell made of frozen water mixed with dust. Below that shell, there is more ice and dust, along with gases like carbon dioxide, carbon monoxide, and nitrogen. In the cold of the outer solar system, these gases remain frozen much of the time, locked into the ice. But ice is not as simple as it seems. Over long periods, radiation from the sun and from space can slowly alter the crust. Parts of it may darken and become less reflective, absorbing more of the weak sunlight. Some ices can slowly turn directly from solid into gas in a process called sublimation, even at low temperatures. As gas accumulates in pockets beneath the surface, pressure begins to build. For a while, the crust can hold it in. Then, eventually, the pressure becomes too much for the weakened shell to bear. A crack opens, or a plug of material gives way, and trapped gas rushes out, carrying dust and chunks of icy material with it. What erupts is sometimes called cryomagma, a mixture of frozen water, ammonia, salts, and volatile gases like methane and nitrogen that were trapped inside the nucleus. The result is a cold volcano, a burst of material that, while far from hot, is still explosive in its own environment. Because 29P is relatively large, its surface gravity is stronger than that of many smaller comets. The escape velocity, the speed something must reach to break free from its pull, is higher. That means that not all of the material thrown upward in an outburst gets away. Some of it falls back, raining down over the surface. As it settles, it can help create a new crust, sealing off the opening and resetting the system for a future eruption. This may be part of why secondary outbursts sometimes follow major ones a few days later. The original blast weakens nearby regions, rearranges the surface, and leaves pockets of gas in new configurations. As the fresh crust forms and pressure redistributes, another crack can open, releasing a smaller burst. Observations of 29P's 2021 activity, with its delayed follow-up eruptions, fit this picture gently but suggestively. Around the nucleus, the ejected particles form a hazy, reflective envelope. Dust and ice grains scatter sunlight, creating a soft cloud that can linger for days or even a couple of weeks. This coma is what makes the comet seem so much brighter after an outburst. To someone watching through a telescope, 29P swells and glows, its little world temporarily wrapped in a luminous scarf. 29P is not alone in being cryovolcanic. Other comets, like 12P, sometimes nicknamed the Devil Comet because of horn-like plumes that appear during its outbursts, show similar behavior. Many of these objects travel on highly elliptical orbits around the Sunday. They spend most of their time far away, then dive inward, warming rapidly as they approach the inner solar system. As you might expect, their activity increases dramatically when they are closest to the sun and feeling the strongest heat. That is part of what makes 29P so puzzling. Its orbit is nearly circular. It stays at roughly the same distance from the sun all the time. The amount of solar energy it receives does not swing wildly up and down. If its behavior were driven purely by sunlight, you might expect its outgassing and eruptions to follow a fairly regular pattern, tied to small variations in its distance from the sun or to steady, slow changes in its surface. Instead, the comet's activity is erratic. Some outbursts are huge, some are small, some come close together, others are spaced more widely apart. The timing is not neatly tied to anything obvious, at least not at first glance. It is a restless object that does not seem to be responding to a simple external rhythm. Still, patterns whisper at the edges of the data, and scientists keep listening for them. One idea that has attracted attention is that 29P's eruptions might be linked to its own rotation. The comet appears to spin slowly, taking roughly 57 days to turn once. As different regions of its surface face the sun, warm and cool, certain pockets of gas might reach their breaking point. When astronomers examined records of the major outbursts, they noticed that many of them seemed to cluster with a spacing of about 52 to 60 days, close to the suspected rotation period. Smaller events also showed hints of repeating intervals, around 30 days for some, around 90 days for others. The pattern is not perfectly regular, and the data are noisy, but there is enough structure to suggest that something like a seasonal cycle might exist on this tiny, icy world of faint echo of weather, tied not to months, but to the turning of the comet itself. Even so, 29P resists being neatly predicted. Its eruptions are often described as quasi-periodic. They happen with some loose regularity, but the exact timing and intensity of any given outburst are still hard to forecast. It is like listening to someone breathing in their sleep. You can sense a rhythm, but you cannot say exactly when the next sigh will come or how deep it will be. That uncertainty has not stopped astronomers from trying. In April 2023, observers noticed that the light surrounding 29P's nucleus had become fainter than they had ever seen before. The coma had thinned. The rate of gas escaping seemed to have slowed. To some researchers, this looked like the calm before a storm. If less gas was escaping now, perhaps more was building up beneath the surface, raising the internal pressure. The comet, they thought, might be quietly charging up for another eruption. They decided to say so out loud. An outburst was likely soon, and then, very quickly, the comet answered. Later that same day, 29P produced a small eruption, a mini outburst compared to some of its larger fits, but still a clear and measurable event. For the first time, a prediction of activity on this strange, volatile little world had come true in real time. It felt like being let in on a secret, just a little. The randomness was not absolute. There was, perhaps, a way to listen to the pressures building beneath the crust, and guess when the next breath of gas would break through. Another piece of the puzzle has been the search for what exactly is driving these eruptions at the chemical level. For a long time, astronomers could not detect carbon dioxide in the environment around 29P. Carbon monoxide, on the other hand, was consistently found in high amounts. It was simple to imagine that this gas, with its ability to sublimate even in the cold outer solar system, was the main engine behind the comet's behavior. Pockets of frozen carbon monoxide warming and turning to gas seemed like a natural source of pressure. The absence of clear carbon dioxide detections left a gap, a quiet question. If carbon monoxide is the main driver, is it acting alone, or is there more to the story hiding below our thresholds of sensitivity? New instruments, like the James Webb Space Telescope, have begun to push those thresholds lower, offering the possibility of seeing fainter signatures and teasing out the roles of different ices more clearly. For now, though, the picture remains one of a restless, cryovolcanic body, where carbon monoxide has long taken center stage, and carbon dioxide has, until recently, stayed in the wings, waiting for a more sensitive ear to hear its part in the song. When astronomers first studied Centaur 29P, carbon monoxide really did seem to be the star of the show. Almost every careful observation of its thin gas halo pointed to this one volatile as the main driver of its restless behavior. For a while, it was tempting to imagine that the story was simple. Frozen carbon monoxide deep inside the comet warmed, turned to gas, and burst out, creating those sudden outflows of dust and light. But in 2024, the James Webb Space Telescope quietly let us know that this was only half the truth. Earlier radio observations had already revealed a narrow jet of carbon monoxide gas pointing roughly in Earth's direction, like a vent on the surface aimed toward us. Webb, with its sensitive near-infrared spectrograph, was able to look more closely at the same region. Instead of a single jet, it found two distinct plumes of carbon monoxide, one still aimed toward Earth, and another pointing off toward the north, tilted slightly away in space. It was as if 29P had opened not one window, but two, letting gas escape from different parts of its surface or from slightly different depths below. And that was not all. Webb also picked up the first clear signs of carbon dioxide on 29P, two jets of it, one emerging from the north and one from the south. These gentle but definite detections were the first solid confirmation that carbon dioxide plays a part in the comet's activity. Suddenly, 29P looked less like a simple, single-vent world and more like a patchwork of active regions, each with its own blend of ices and gases, each breathing in its own way. The way these gases are arranged tells its own quiet story. The different amounts of carbon monoxide and carbon dioxide in the various jets hint that 29P might not be a single uniform block of ice and rock. Instead, it may be made of several pieces that have become stuck together over time, a cluster of smaller bodies pressed into one. Each piece could carry its own internal history and mixture of ices, so that when gas escapes, the composition of one vent does not exactly match that of another. Even with this new clarity, one big question remains. What exactly is feeding those high levels of carbon monoxide? Carbon monoxide is extremely volatile. Pure carbon monoxide ice can sublimate, that is, turn directly from solid to gas at temperatures as low as about 25 kelvins, only a few dozen degrees above absolute zero. If large amounts of it were sitting near the surface of 29P, Exposed to the weak sunlight at its current distance from the sun, it should have evaporated a long time ago. The fact that it is still present in such abundance suggests that it must be stored more deeply, held in some kind of protective structure. One of the most intriguing ideas points to a special form of water ice, amorphous ice. Almost all the ice we encounter in everyday life on Earth is crystalline. In crystalline ice, the water molecules arrange themselves in a regular, ordered pattern, like a neat grid of tiny bonded neighbors. Amorphous ice is different. Its molecules are jumbled and disordered, more like a crowd than a crystal. Because they are not packed as efficiently, amorphous ice is less dense than crystalline ice, and its tangled structure leaves tiny spaces where other molecules like carbon monoxide can become trapped. At very low temperatures, this amorphous form can survive for a long time, but as it warms, it naturally tends to rearrange itself into the more orderly crystalline structure. This transformation begins at temperatures above roughly 77 kelvins, and the warmer it gets, the faster the change proceeds. When amorphous ice crystallizes, it can no longer hold on to the gases threaded through it. Those trapped molecules are squeezed out, forced to find a way out of the solid that once held them. If Centaur 29P still carries a core rich in amorphous ice, laced with carbon monoxide and other gases, and if that ice is slowly converting into crystalline form, then the conversion itself could be the source of the comet's persistent carbon monoxide. As the ice reorganizes, gas is released, moving through cracks and pores until it escapes as a jet. To see how this might work, it helps to trace the path 29P has taken. Long ago, 29P likely started its life in the Kuiper Belt, a distant ring of icy bodies beyond Neptune. Out there, temperatures are frigid, around 30 to 40 kelvins. At those temperatures, any water ice present would naturally form in the amorphous state. Over millions of years, faint gravitational nudges from the giant planets slowly shifted 29P's orbit inward. Today, it circles the Sun at a distance of about 6 astronomical units, roughly 6 times the distance between Earth and the Sunday. In that region, the typical temperatures are closer to 110, 120 kelvins, warm enough for amorphous ice to begin turning crystalline. The question is not whether this conversion happens, but how long it takes. Researchers looked at several small Centaur's objects, only 1 to 6 kilometers across, on orbits similar to 29P's current path. Using models of heat flow and ice behavior, they estimated how long it would take for any amorphous ice inside these small bodies to fully crystallize. The answer was surprisingly short in cosmic terms, between about 100,000 and 6 million years. That means that by the time such small centaurs settle into orbits like 29P's, their interiors are likely already fully crystalline. Any gases that were once trapped in amorphous ice would have been released long ago. These little centaurs would have no hidden reservoir of pressurized gas left. Their behavior, at least in this respect, should be fairly quiet and predictable. But 29P is not small. With a diameter of about 60 kilometers, it is dramatically larger than those examples. Its bulk changes everything. When scientists ran the same kinds of calculations for an object the size of 29P, they found that the timescale for complete crystallization stretched out dramatically. Instead of a few million years, it might take between 60 and 100 million years for all of the amorphous ice in such a large body to convert. If 29P has only been in its present, warmer orbit for around 10 million years, That would mean it is still in the middle of the process. Some estimates suggest that only about half to two-thirds of its amorphous ice has crystallized so far. If that is true, an important consequence follows. Deep inside 29P, there may still be extensive regions of amorphous ice filled with trapped gases that have not yet been released. As the conversion front slowly moves inward, outer layers crystallizing first, inner layers later, new reservoirs of gas are continually being squeezed out and forced to migrate. This could provide a long-lasting source of carbon monoxide and other volatiles, feeding eruptions over tens of millions of years. The change from amorphous to crystalline ice does more than just release gas. Because amorphous ice is less dense, turning it into the denser crystalline form shrinks the volume of the material. Imagine parts of the comet's interior quietly contracting as the ice reorganizes. That slow, uneven shrinking can put stress on the surrounding structure. Cavities may open, overhangs might become unstable. Sections of the interior could collapse. Some researchers think that these structural failures, cave-ins, landslides, sudden sinkholes forming under the surface could be the triggers for many of 29P's outbursts. A collapse might break open a sealed pocket of gas-rich material, suddenly connecting it to the surface and giving the gas a pathway to escape. In that moment, pressure that had been building invisibly for a long time can rush out all at once, carrying dust and ice with it in a spray. The result, seen from afar, is a brief but powerful flare in brightness. It is an elegant picture, a large centaur with a half-converted interior, full of stressed layers and hidden voids, its crust occasionally giving way and allowing trapped gases to explode outward. But even this story does not answer every question. One of the lingering puzzles is how 29P manages to erupt so often and, at times, in such quick succession. The comet does not just leak gently, it produces multiple explosive events within a single year, and occasionally several within days. For pressure to build up quickly enough to fuel repeated blasts, the internal plumbing must be complex, full of separate pockets, channels, and blocked vents that we can only guess at. We still do not know exactly how gas moves inside the nucleus, how the small-scale structure is arranged, or how one eruption might set the stage for the next. The bursts of brightness we see from Earth are the visible skin of a much deeper, hidden process. So, for now, Centaur 29P keeps some of its mysteries. We know more than we did. That carbon dioxide is present alongside carbon monoxide, that multiple jets can operate at once, that amorphous ice and long timescales can help explain the high gas levels. We have a clearer sense of how a body born in the Kuiper Belt might arrive here, still holding pockets of volatile material, but we do not yet have a complete map of how all those ingredients fit together. In a way, that is part of the comet's quiet charm. It reminds us that even in the cold outer reaches of the solar system, far from the sun's warmth, icy worlds can be surprisingly fiery inside. Their behavior can challenge our assumptions, asking us to imagine interiors that crunch, crack, and breathe in ways we are only beginning to grasp. And as our instruments become more sensitive and our models more refined, we keep returning our attention to 29P, listening for each new outburst as if it were another line in an ongoing, slowly told story. Little by little, we are starting to untangle the behavior of strange objects like Centaur 29P. Each new instrument, from ground-based telescopes to delicate eyes in space like the James Webb Space Telescope, adds another thread to the picture. And every thread, if you follow it far enough, seems to lead outward past the orbits of the giant planets, past the familiar belts of debris, toward the very edge of the sun's reach. Out there, at the outskirts of our solar system, lies a structure we have never seen directly, but which may quietly cradle the origins of many of the comets that fall inward toward our skies. Imagine a vast, almost unimaginable shell that begins where the solar system seems to thin out and then keeps going. Not a solid wall, but a loose, ghostly bubble made of ancient ice and dust. Billions, perhaps trillions, of frozen chunks, some as large as mountains, all drifting in slow orbits around the Sunday. This is the Oort cloud, or at least the idea of it, a hypothetical sphere of icy bodies marking the farthest boundary where the sun still holds sway. If you could see it from far away, our solar system would not look like a flat disk with a few rings. It would look like a tiny glowing center wrapped in a deep, almost invisible cocoon of comets. The distances involved are so huge that even our most powerful telescopes cannot pick out individual objects there. The Oort cloud, if it exists as we think, is far beyond the reach of sharp images. It lives in a realm where the sun's light is dim and thin, and the pull of other stars and the Milky Way's tide begin to tug as strongly as our own star does. It is a borderland between the solar system and interstellar space, more a whisper than a solid edge. So if we have never seen it, why do astronomers think it is there at all? How can you talk about a cloud no one has ever directly observed? The path to that idea begins much closer in, with structures you may have already heard of, the asteroid belt and the Kuiper belt. Both are roughly ring-shaped regions that circle the sun in the same broad plane as the planets, like faint donuts made of rock and ice. The asteroid belt sits between Mars and Jupiter. It is made up of millions of rocky bodies, leftovers from the early days of planet formation that never fully merged into a single world. These asteroids move mostly in the same direction and share roughly the same orbital plane as the planets, like a thickened, broken ring. Farther out, beyond Neptune, lies the Kuiper belt. Astronomers like Gerard Kuiper suggested its existence in the mid-20th century as a likely home for the so-called short-period comets, comets that take less than about 200 years to complete one loop around the Sunday. The Kuiper belt is a broad field of icy debris extending from about 30 astronomical units, AU, to roughly 50 AU. 1 AU is the distance from Earth to the Sun, about 150 million kilometers. So, the Kuiper belt begins where Neptune orbits at around 30 AU and stretches out a bit beyond that. Pieces of Kuiper belt material do not usually stay forever in their original paths. Gravitational nudges from Neptune and the other giant planets can disturb them. Every so often, a small, icy body is sent inward on a new, more elongated orbit. When this happens, the sun can warm its surface enough to release gas and dust, sprouting a coma and tail. A short-period comet is born. Because these orbits are relatively tight, such comets return on human timescales, decades or centuries, and we can predict when some of them will come back. Halley's Comet, for instance, with its period of about 75 years, is one of these repeat visitors. So is Encke's Comet, which completes a circuit in just a little over 3 years. While Gerard Kuiper and others were thinking about these short-period comets and their origin in a flattened outer belt, another astronomer in the Netherlands was puzzling over a different kind of visitor. His name was Jan Oort, and his contributions to 20th century astronomy were remarkably wide-ranging. In the 1,920 seconds, he helped determine where in the Milky Way our sun is located, placing us within the swirling disk of our galaxy. In the early 1,930 seconds, he provided some of the first evidence that there must be unseen mass, what we now call dark matter, affecting the motions of stars. He had a talent for looking at patterns and seeing the invisible structures they implied. By the middle of the century, Oort turned his attention to comets with very long periods. These were not the regular, predictable visitors like Halley. Some of them had orbital periods measured not in decades, but in millions of years. A few, based on their paths, might take tens of millions of years to complete a single loop around the Sunday. Others would appear once and, as far as we can tell, never return again. These long-period comets had another odd feature. They did not arrive from the same flat band of space as the planets and the Kuiper Belt. Instead, they came from all directions, from above the solar system, from below, from angles tilted at every possible inclination. If you drew their paths, they would form a loosely filled sphere of incoming tracks, not a disk. This posed a puzzle. If these comets were not arriving from interstellar space and not from the Kuiper Belt, where were they coming from? Oort carefully studied the orbits of many long-period comets and noticed something subtle but important. When you describe an orbit, there is a point where the object is closest to the Sun, the perihelion, and a point where it is farthest away, the aphelion. For these comets, he found that their aphelia, those farthest points, tended to cluster around a particular distance, not scatter randomly across all scales. That distance was enormous. When he converted it into kilometers, it came out to around 7.5 trillion kilometers from the Sunday. Numbers that large are hard to hold in the mind, so astronomers often use AU instead. Dividing by the distance from Earth to the Sun, Oort found that the aphelia of these long-period comets grouped around about 50,000 AU. To get a sense of what that means, remember that Neptune orbits at about 30 AU. The main Kuiper Belt stretches from roughly 30 to 50 AU. So 50,000 AU is 1,000 times farther out than the outer edge of the Kuiper Belt, and more than 1,600 times farther than Neptune. If the distance from the Sun to Neptune were the width of a room, the characteristic radius of Oort's proposed cloud would be like walking more than a kilometer away. Oort also noticed another important detail. The orbits of these comets, traced backward in time, did not look like paths of objects that had wandered in from the empty space between stars. Instead, their shapes suggested that they had been gravitationally bound to the Sun all along. They were part of the solar system, just on orbits so vast that they carried them far out into regions where the Sun's pull was weak and fragile. Putting these clues together, the grouping of aphelia around 50,000 AU, the spherical distribution of incoming directions, and the indication that the comets were still tied to the Sun, Oort proposed something bold. He suggested that there must be an enormous, roughly spherical cloud of icy bodies surrounding the solar system at those distances. This cloud would be the source of long-period comets, a reservoir that occasionally sends one inward when its orbit is gently disturbed by the gravity of passing stars or the collective pull of the galaxy itself. Unlike the asteroid belt or the Kuiper Belt, this structure, would not be a flat ring in the plane of the planets. It would be a three-dimensional halo, reaching in every direction, like a faint fog of comets encasing the Sunday. Today, we call this hypothetical region the Oort cloud, in his honor. Since Oort's original proposal in 1950, other discoveries have filled in more detail. Spacecraft like NASA's New Horizons, which flew past Pluto and continued into the Kuiper Belt, have gathered evidence for a second, more diffuse component of that belt, known as the scattered disk. This scattered population of icy bodies extends well beyond the main Kuiper Belt, perhaps out to around 1,000 AU. Their elongated orbits and tilted paths appear to be stepping stones between the orderly inner regions and the much more remote domain of the Oort cloud. Mathematical models of how the solar system formed and evolved, including the early migration of the giant planets, also tend to produce something like an Oort cloud, almost as a byproduct. In these simulations, countless small, icy planetesimals are flung outward by close encounters with Jupiter and the other giants. Some are lost to interstellar space altogether. Others are thrown onto extremely long, loosely bound orbits that carry them far away but keep them just barely tethered to the Sunday. Over billions of years, their paths are stirred by the gravity of passing stars and the galaxy's tides until they fill a roughly spherical shell. We still have not directly imaged a single Oort cloud object. They are simply too small and too far away for present instruments. But every time a new long-period comet is discovered and its orbit traced backward, it adds one more dot to the picture Oort first sketched, a pattern of paths that, taken together, point to a hidden, icy halo far beyond what we can see, in the dark beyond Neptune and the Kuiper Belt. Then, the solar system seems to end not with a hard boundary, but with a fading of influence, a region where the sun's pull is gentle and the comets drift on timescales longer than all of human history. Somewhere out there, in that unseen shell, future comets are waiting, their ice is still asleep. One day, a few of them will be nudged inward, beginning journeys that might, millions of years from now, end with a soft brightening in someone's night sky, and perhaps with another step in our long, patient effort to understand where they came from. The leading idea about the Oort cloud is quietly simple and very old. It says that this vast, distant shell did not appear out of nowhere, but grew from leftovers, the ancient debris that remained after the planets of our solar system formed about 4.6 billion years ago. In the early days, the sun was surrounded by a thick disk of gas and dust. From that disk, small, solid clumps began to form, sticking together grain by grain, then pebble by pebble, until some of them became larger bodies called planetesimals. Over time, some of these planetesimals grew big enough to become the cores of planets. Others remained in between, too small to be worlds, too large to be dust, drifting like building blocks that never found their final place. When the giant planets Jupiter, Saturn, Uranus, and Neptune took shape, their gravity changed everything. Instead of a quiet disk, the outer solar system became a place of close encounters. As these massive young planets moved through the leftover debris, their pull scattered the remaining planetesimals in all directions. Some of the small bodies were sent inward, where they either collided with other worlds or were broken apart. Some were flung outward completely, their paths altered so much that they escaped the sun's influence and were lost to interstellar space. But not all of them went quite so far. A significant number were thrown onto long, stretched out, eccentric orbits. These paths carried them far from the sun, into regions where our star's gravity was weak but still present. Their orbits were eccentric enough that the pull of other forces passing stars, great clouds of gas in the galaxy, and the tidal tug of the Milky Way itself could gently reshape them over time, while still leaving them technically bound to the Sunday. These scattered planetesimals are thought to be the seeds of what we now call the Oort cloud. Billions, or even trillions, of icy chunks arranged in a loose, distant halo. In the more familiar region closer in, gravitational nudges can push Kuiper Belt objects off their stable paths, sending them inward as short-period comets with orbits of less than about 200 years. We think something similar happens in the far outer regions, just on a much grander scale. For Oort cloud objects, those same kinds of perturbations, tiny changes in their orbits over huge stretches of time, can turn nearly circular or gently stretched paths into highly elongated ellipses that dive toward the inner solar system. When that happens, a piece of the Oort cloud becomes a long-period comet, taking hundreds of thousands or millions of years to complete a single orbit. What can cause such perturbations? Out there, far from the sun, the whole galaxy becomes a kind of delicate sculptor. A star passing within a light year or so can add a small tug. A massive cloud of gas and dust drifting in the Milky Way can pull just enough to tilt or stretch an orbit. Even the overall tidal field of the galaxy, the way gravity changes from one place to another, can slowly shift these distant bodies, one tiny step at a time. We have even caught a glimpse of this kind of encounter in our own cosmic neighborhood. About 70,000 years ago, a blink of an eye on geological timescales, but older than any written human story, a small binary system known as Schultz star passed unusually close to our solar system. It did not plunge through the region of the planets, but it seems to have grazed the outermost parts of the Oort cloud. Schultz's star is a low-mass pair, a red dwarf accompanied by a brown dwarf. Compared to our Sun, it is small and light, its gravity far weaker. Even at its closest approach, its pull on the Oort cloud would have been modest compared to the Sun's stronger grip. That is one of the reasons nothing dramatic happened in our skies. There was no sudden storm of comets, no catastrophic disruption of the solar system. Still, numerical simulations published in 2018 suggest that this brief encounter probably did have some effect. While most Oort cloud objects felt almost nothing, a small fraction may have had their orbits nudged, altered just enough to begin long, slow journeys inward, eventually becoming some of the long-period comets we see today. It is a soft reminder that the space around our Sun is not truly empty. Other stars pass by from time to time, each one leaving a subtle fingerprint. Of course, the Sun has been shining for more than 4 billion years. That is a long stretch of time for such close passages and mild gravitational brushes to occur. You might wonder whether so many encounters would have prevented the Oort cloud from forming at all, whether repeated disturbances would simply strip away all the distant debris. Our best models say no. The same interactions that can sometimes remove material can also build and refill the cloud. Over eons, some Oort cloud objects may be captured from other stars, while some of ours might be handed off to neighboring systems. In this view, the Oort cloud is not a static shell, but part of a slow, quiet exchange between stars as they drift through the galaxy, carrying their own distant swarms of icy bodies. Recent simulations support the idea that other stars may have Oort clouds of their own. When planetary systems form in clusters, Stars are born close together. In those early, crowded environments, their gravity can mix small bodies freely. A newborn star might pick up planetesimals from its siblings, then carry them outward as it drifts away. Over time, these objects can populate a cloud similar to our own, an outer reservoir of comets waiting in the deep freeze. Our Oort cloud may be more layered and structured than a simple hollow sphere. Some scientists suggest it has both an inner and an outer region. The inner part, closer to the sun, could be somewhat flattened, more like a thick, distant disk, a faint echo of the Kuiper Belt's donut shape, but at far greater distances. The outer part, extending almost to the point where the sun's influence fades into the galaxy's background field, is thought to form the more spherical shell we most often picture when we speak of the Oort cloud. Taken together, these two regions may stretch from perhaps 2,000 astronomical units at the very innermost edge, all the way out to around 100,000 AU. That outer boundary is not sharp. It is more like a gradual fading of our star's influence. But if you treat that as a rough measure, it means the Oort cloud could span more than 1.5 light-years across, large enough that if you started in the middle, at the sun, you would travel a significant fraction of the distance to the nearest stars before leaving it behind. To feel just how far that is, it helps to think about one of our own emissaries into space, the Voyager 2 spacecraft. Voyager 2 was launched from Earth at 1 AU from the Sun in August of 1977. Since then, it has traveled outward at about 56,000 kilometers per hour, covering an average of around 3.3 astronomical units each year. Over decades, it visited Jupiter, Saturn, Uranus, and Neptune, sending back images and data, and then kept going. As of now, it has reached a distance of roughly 139 AU from the Sunday. That makes it the second farthest human-made object, just behind Voyager 1. Along the way, Voyager 2 passed through the boundary of the heliosphere, the region dominated by the sun's constant outflow of charged particles, known as the solar wind. The heliosphere stretches far beyond the planets, expanding until the solar wind is slowed and finally pushed back by the thin gas and magnetic fields of interstellar space. In August 2007, Voyager 2 crossed the termination shock, where the solar wind first slows abruptly. In November 2018, it passed through the outermost turbulent layer, the heliosheath, and entered the local interstellar medium. At that point, it had truly left the sun's protective bubble, sailing into the space between the stars. And yet, even now, long past the main Kuiper Belt and well beyond the heliosphere, Voyager 2 is still only a fraction of the way to the Oort cloud. At its current speed, it would need roughly another 300 years just to reach the inner edge of the cloud, if it happens to be heading in the right general direction. To pass all the way through, from one side to the other, could take on the order of 30,000 years. Moving at tens of thousands of kilometers per hour sounds fast when you compare it to a car or an airplane, but on the scale of light years, it is a gentle crawl. Over the course of those same 30,000 years, the stars around us would also shift. Our nearest stellar neighbor, Proxima Centauri, is a little more than 4.2 light-years away. Even that close distance is vast compared to the size of our own planetary system. When people talk about the difficulty of interstellar or intergalactic travel, this is part of what they mean. The space between stars is not just empty, it is enormous. Given these scales, it is perhaps not surprising that some people still question the existence of the Oort cloud. If we cannot see it directly, and if it lies so far out that even our fastest spacecraft will not reach it for many human lifetimes, might it be an illusion? Could long-period comets be arriving from somewhere else instead, perhaps from deep interstellar space or from other stars' own debris fields? There is some evidence that at least a few comets do come from beyond the sun's grasp. In 2019, an amateur astronomer named Gennady Borisov discovered a faint, fast-moving object that did not follow the usual paths of solar system comets. Its orbit was hyperbolic, too open to be tied to the sunday. This comet, later named Borisov in his honor, turned out to be our first well-studied example of an interstellar comet, a visitor formed around another star, passing briefly through our neighborhood before heading back into the galactic dark. Professional astronomers quickly turned their instruments toward Borisov, gathering spectra and measuring its brightness. They found that its composition was unusual compared to many comets born in our own system. In particular, it seemed to have a higher concentration of carbon monoxide than average, hinting that it might have formed in a colder environment or under the influence of a different kind of star, perhaps a red dwarf. It was a fascinating example of how diverse cometary chemistry can be, and a reminder that not every icy traveler we see necessarily belongs to the Sunday. Even so, the vast majority of astronomers think that interstellar comets like Borisov are rare exceptions, not the main source of long-period comets. The patterns in the orbits of most long-period comets, the way their aphelia cluster around certain distances, the directions from which they arrive, the numbers we see over time, all line up more naturally with an Oort cloud origin than with random arrivals from the galaxy at large. In this sense, the Oort cloud is a bit like the heliocentric model was in Copernicus's time, an elegant explanation supported by many lines of indirect evidence, even though direct visual proof remains out of reach. Our telescopes can see bright stars hundreds of light years away and trace the shapes of galaxies millions of light years distant, but those objects are enormous and luminous. An Oort cloud body is likely no bigger than a mountain. If you picture a single piece of Oort cloud debris as something roughly the size of Mount Everest, about 9 kilometers tall, you can start to feel the challenge. Place that icy mountain more than 50,000 astronomical units away. Let it reflect hardly any light from a distant sun, and then try to spot it from here. It is no wonder that, for now, the cloud it belongs to remains invisible, known not by direct sight but by the quiet, graceful arcs of the comets that sometimes fall from it toward our inner, sunlit skies. If you let your imagination drift outward from the sun, there comes a point where familiar distances begin to lose their meaning. The inner edge of the Oort cloud is thought to begin around 3,000 astronomical units from our star, far beyond the orbit of Neptune, far beyond the main Kuiper belt, out where the sunlight is a pale whisper. At that distance, even the nearest chunk of Oort cloud material would be unbelievably far from the sun compared to its own tiny size. The ratio is staggering. The distance from the sun to that little body is tens of millions of times larger than the object itself. Trying to find one of these icy specks directly is like searching for a single grain of sand from across an ocean with only a weak flashlight in your hand. There is another difficulty, just as important. Stars and galaxies shine with their own light. Even the planets, though dark inside, sit close enough to the sun that they reflect its light back toward us, glowing faintly against the black. The same is true of the asteroid belt and the Kuiper belt. Those regions are still within a range where sunlight, though weaker than on Earth, is strong enough that icy and rocky surfaces can scatter it into our telescopes. The Oort cloud, if it exists as we think, lies mostly beyond the protective bubble of the heliosphere, the region where the solar wind dominates. Out there, the sun's light is thin and distant. Small, dirty ice balls the size of mountains receive so little illumination that they may as well be invisible against the backdrop of space. They do not shine, they do not glow. They simply drift, black on black. So for now, even with our most sensitive instruments, the Oort cloud is too far and too dark to capture in a direct picture. Despite its enormous footprint and the way it helps us make sense of long-period comets, we know it only through hints, mathematical models, the orbits of the comets that fall inward, the way those orbits cluster at certain distances and arrive from every direction. It can feel unsatisfying, this idea of a structure we cannot yet see. But science has grown used to walking in the half-light, following patterns long before direct proof arrives. There have been other times when the universe asked us to trust indirect evidence. In the 16th century, Nicolaus Copernicus suggested that Earth and the other planets circle the sun, not the other way around. In the early 17th century, Galileo Galilei took that idea seriously, watching the motions of Jupiter's moons and the phases of Venus, and realized that the old picture with Earth at the center of everything could not explain what he saw. Neither of them could step outside the solar system and look back to check. They had no spacecraft, no cameras orbiting the Sunday. Their heliocentric model was built from careful observation of motions in the sky, from geometry and patience. It was a theory about the unseen structure underlying what they could measure. Only much later did our rockets and probes and satellites give us the kind of vantage point they could only dream of. When they did, the view matched the pattern those early thinkers had traced. The Oort cloud sits in a similar place in our understanding. It is a way of making sense of long-period comets, of their distances, their directions, their speeds. The farther we move through time, the more likely it becomes that new tools will push our vision outward. A century from now, other astronomers may look back on our era the way we look back on Copernicus and Galileo, as a time when the structure was mostly inferred and only partly seen. Perhaps by then, someone will have found a way to detect individual Oort cloud objects directly by their faint heat or by the way they block the light of distant stars as they pass in front of them. Or perhaps a new explanation for long-period comets will emerge, something that reshapes our mental picture once again. For now, the Oort cloud remains one of astronomy's quietest riddles, a vast, invisible halo of potential comets drifting in a darkness we have not yet learned to fully read. If you trace a path from here to there, from Earth's orbit out into that deep freeze, it becomes a journey through layers of memory. You would begin near the sun, slipping past the inner rocky planets, Mercury, hot and airless, Venus with its thick clouds, Earth, blue and bright, Mars, dry and rust-colored. Beyond Mars lies the asteroid belt, a loose, sprawling ring of rocky bodies. It stretches from about 2.2 to 3.2 astronomical units from the Sun, a region roughly 1 AU wide. 1 AU, remember, is the distance from Earth to the Sun, about 150 million kilometers. Most of the known asteroids live in this zone. Some are hundreds of kilometers across, like Vesta, whose width is comparable to the distance between two distant cities on Earth. Others are only tens of kilometers wide, irregular and battered. Despite their numbers, the combined mass of all the asteroids in the belt is just a tiny fraction of the Moon's mass, only a few percent. Spread out over such a large volume, they form a population that is sparse rather than crowded. Beyond the asteroid belt, the solar system opens out into the realm of giants. Jupiter, Saturn, Uranus, and Neptune dominate this region, huge worlds of gas and ice that hold most of the planetary mass. Their storms and rings and magnetic fields are their own deep stories. For our journey, they serve as milestones, great signposts on the way outward. Passing Neptune's orbit at about 30 AU, you cross into another kind of frontier. Here, in the dim outer sunlight, lies the Kuiper Belt, a vast ring of icy debris encircling the solar system like a frozen halo. The Kuiper Belt is not just a scattered collection of cold rocks. It is a time capsule. The objects that inhabit it, Kuiper Belt objects, or KBOs, are among the oldest surviving pieces of the solar nebula, the original disk of gas and dust from which the planets formed 4.6 billion years ago. In their frozen interiors, they may still preserve the proportions of ices and dust that were present before worlds like Earth, Jupiter, and Neptune assembled. The belt stretches from about 30 to 50 AU, though its influence blurs at the edges. Within it reside dwarf planets like Pluto and several others, along with countless smaller bodies. Some follow neat, nearly circular paths. Others move on more eccentric or inclined orbits, their positions subtly shaped by past interactions with Neptune. For a long time, this region was purely theoretical. Pluto, discovered in 1930, seemed at first to be a solitary wanderer in the outer dark, a lonely dwarf planet circling beyond Neptune. Its small size and strangely tilted orbit, though, made some astronomers suspect that it might not be alone, that it could instead be the largest member of a much broader population of icy worlds. In 1951, Gerard Kuiper proposed just such a belt of objects, but in those decades, our telescopes were not yet sensitive enough to pick out faint, small bodies so far away from the Sunday. The idea lingered as a possibility, supported by theory but not by direct sightings. That changed in 1992. Astronomers David Jewett and Jane Liu were systematically searching the sky for distant, slow-moving points of light. After years of patient work, they identified an object beyond Neptune that was not Pluto and not a known planet or asteroid. It was given the provisional name 1992 QB1 and became the first confirmed Kuiper Belt object. In a way, Pluto and its large moon, Charon, could only truly be recognized as KBOs after that moment. They had been discovered earlier, Pluto in 1930, Charon in 1978, but it was the detection of 1992 QB1 that proved the belt itself was real. Since then, thousands of KBOs have been cataloged, filling out the Kuiper Belt into a rich, varied population. To feel the scale of this region, you can imagine again that you are gliding outward in a small, quiet spacecraft. You leave the sun behind as a bright disk and watch it shrink into a brilliant star. You pass the orbits of the inner planets, the asteroid belt, the gas giants. Somewhere around 30 AU, the landscape of orbits changes, and you enter a sparse but steady sea of icy bodies. Compared to the Oort cloud, the Kuiper belt is close and almost friendly. Its objects are near enough that we can see some of them directly through our telescopes and even send spacecraft to visit. New Horizons, for instance, flew past Pluto and Charon, then continued on to study another KBO up close. The images it sent back revealed surfaces shaped by ice, sunlight, and time, plains of frozen nitrogen, mountains of water ice, complex patterns carved by exotic frosts. And yet, even here, much remains unknown. Many of the smaller KBOs are little more than points of light, their sizes and shapes inferred from how they reflect sunlight. Each one is a small archive of early solar system material, locked away in a deep freeze since long before Earth had oceans or air. If you kept flying outward from the Kuiper belt, past 50 AU and beyond, you would eventually enter the scattered disk, a region of more eccentric and inclined orbits, and, much farther still, the realm where Oort's invisible cloud is thought to begin. Somewhere in that distant dark, the last of the sun's building blocks, untouched and unchanged, drift in silence. Between these regions, the bright inner planets, the rocky asteroid belt, the icy Kuiper belt, and the ghostly Oort cloud, the solar system tells its story in layers. Each one preserves a different phase of our cosmic home's youth. The fact that some of those layers remain invisible to us does not make them less real. It simply means that we are still in the early chapters of understanding, still piecing together the outline of something vast and intricate, one faint signal at a time. Far out beyond Neptune, there is a region where the sun is little more than a bright star, and daylight is a very gentle thing. Here, in the Kuiper belt, countless icy bodies circle in the dark, held in place by the gravity of a star that now feels very far away. Long ago, this region might have been on its way to forming another planet. There was enough material ice, frozen gases, dust for something large to accrete, but Neptune's gravity stood in the way. Its pull stirred and disturbed the orbits of the icy objects beyond it, preventing them from settling into a single, growing world. Instead of coming together, they stayed apart, a population of small bodies that never quite managed to become one. Unlike the asteroid belt closer in, which is made mostly of rocky material, the Kuiper belt is dominated by ice. Its objects are rich in frozen methane, ammonia, and water, forming a thick, cold ring of debris. If you could scoop up a handful of Kuiper belt material, it would be more like dirty snow than stone. This ring is anything but empty. The Kuiper belt is thought to contain hundreds of thousands of sizable icy bodies larger than 100 kilometers across, along with more than 1 trillion comets and an untold number of smaller fragments and dust grains. And yet, despite that abundance, the distance between individual objects is so vast that it almost defies imagination. On average, neighboring bodies are separated by something like 0.02 to 0.1 astronomical units, millions upon millions of kilometers. You can picture each icy world as a lonely traveler, with perhaps 10 million kilometers of quiet space between it and its nearest neighbor. Out here, collisions are rare. These objects drift in near silence, slowly tracing their paths around the sun, preserving in their frozen interiors clues about how planets and comets once began. The main Kuiper belt, the region most people think of first, extends from about 30 to 50 astronomical units from the Sunday, but it is not the whole story. Beyond its outer edge lies a more diffuse, more chaotic zone called the scattered disk. Here, some objects follow highly elongated orbits that can reach out to nearly 1,000 AU, and a few stretch even farther. These scattered objects have been tugged and tilted by past encounters with Neptune, their paths more erratic than those of the more orderly Kuiper Belt residents. Side by side, the asteroid belt and the Kuiper Belt share a simple similarity. Both are rings of debris left over from planet formation, but their scales are very different. The asteroid belt is a narrow band in the inner solar system, a thin ring between Mars and Jupiter. The Kuiper Belt is a broad, distant halo of ice, far more extensive and spread out, stretching over a region many times wider and much farther from the Sunday. And even the Kuiper Belt is not the outermost structure shaped by our star. Enveloping all of this planets, belts, scattered objects is the hypothetical Oort cloud, that colossal spherical shell of cometary debris that may surround the solar system from about a few thousand AU all the way out toward 100,000 AU. While the Kuiper Belt is a relatively close donut-shaped ring, the Oort cloud is thought to be a vast, nearly spherical bubble. One lies thousands of times closer to the Sun than the other's center. Despite these differences in shape and scale, the Kuiper Belt and the Oort cloud share an important role. Both seem to be sources of comets. The Oort cloud likely gives rise to many long-period comets, those with orbits that can take hundreds of thousands of years to complete a single loop. The Kuiper Belt and its scattered disk, by contrast, are thought to be the birthplace of many short-period comets, with orbits shorter than about 200 years. Today, the Kuiper Belt is one of the most massive structures in our planetary system, but it is just a fraction of what it once was. In the distant past, the total mass of the Kuiper Belt may have been 7 to 10 times that of Earth. As the orbits of the giant planets shifted and settled, their gravity scattered much of that material away. Some of it was flung into interstellar space, some drawn inward and swept up or broken apart. What remains now is perhaps no more than about 10% of Earth's mass. Even in its diminished state, the Kuiper Belt is still slowly eroding. Objects occasionally collide, shattering into smaller fragments. Dust created in these impacts can be pushed outward by the solar wind or blown into interstellar space by the gentle pressure of sunlight. Neptune's gravity can nudge some Kuiper Belt objects onto new trajectories that bring them closer to the Sun, transforming them into short-period comets. As these comets repeat their journeys, the Sun's radiation warms them, causing ices to sublimate and stream away. This process creates the glowing comets and tails we see from Earth, beautiful yet transient features that slowly deplete the comet's material. Several of the most famous comets we know appear to trace their origins back to the Kuiper Belt or its scattered disk. Halley's Comet, for example, returns roughly every 76 years, a familiar visitor on a human timescale. Comet Shoemaker-Levy 9, which broke into fragments and collided with Jupiter in 1994, was also thought to have come from this region before being captured by the giant planet's gravity. Its dramatic impact gave us the first clear view of a collision between two major bodies in our solar system, a sobering reminder of how dynamic and sometimes violent this cosmic environment can be. For people on Earth, it is natural to wonder whether all these distant objects pose a danger. Near-Earth asteroids occasionally make the news, and the idea of a comet on a collision course can be unsettling. But the short-period comets born in the Kuiper Belt follow well-studied paths, and none that we know of threaten our world in the near future. Their journeys are part of the slow, ongoing story of the solar system rather than an immediate reason to lose sleep. What makes the Kuiper Belt especially compelling is that, unlike the Oort cloud, we have actually been there with a spacecraft. For a long time, almost everything we knew about this region came from ground-based observatories and the Hubble Space Telescope, faint dots of light slowly shifting against the background stars, tiny clues to size, color, and motion. Then NASA's New Horizons mission changed the picture. Launched in 2006, New Horizons sped past the inner planets, crossed the orbit of Jupiter for a gravity assist, and headed outward at high speed. In 2015, it flew by Pluto and its large moon, Charon, revealing their surfaces in detail no one had ever seen before. Plains of frozen nitrogen, towering mountains of ice, complex patterns etched by time and sunlight. But New Horizons' journey did not end there. After Pluto, it continued deeper into the Kuiper Belt to visit another, even more mysterious object. This second target, originally known as 2014 MU69 and later named Arakoth, a word meaning sky in the language of the Powhatan people, became the focus of the most distant flyby ever attempted. In 2019, New Horizons swept past Arakoth at a distance of only about 3,500 kilometers, while the object itself lay some 1.5 billion kilometers beyond Pluto's orbit. In that moment, for the first time, we saw a small Kuiper Belt object up close. Arakoth turned out to be stranger than almost anyone expected. Rather than a simple sphere or an irregular lump, it is a contact binary, two distinct lobes that gently came together and fused into one. Its shape resembles a flattened snowman or two pancakes pressed end to end. The larger lobe and the smaller one are connected by a narrow neck, giving the whole object a softly sculpted, otherworldly look. In absolute terms, Arakoth is tiny, about 35 kilometers long, 20 kilometers wide, and 10 kilometers thick. It has no atmosphere, no visible weather, and only subtle variations in color on its surface. At first glance, it might seem like a minor character in the solar system's story, but what it lacks in size and complexity, it makes up for in what it can tell us about how worlds begin. Because Arakoth is so far from the sun and has remained in the Kuiper Belt for billions of years, it is thought to be extremely primitive. Its surface appears relatively smooth, with few large craters and no signs of violent shattering. The two lobes seem to have merged at low speed, without the kind of high-energy collision that would leave deep fractures and chaotic rubble. This gentle joining tells us something important about how planetesimals, the building blocks of planets, may have formed. For a long time, there were two main ideas about how small objects come together to make larger ones. In the hierarchical accretion picture, tiny particles collide and stick, gradually building up bigger and bigger bodies. As they grow, their gravity strengthens, and collisions can happen at higher speeds. Over time, this could lead to the creation of substantial planetesimals through many energetic impacts. The other idea is sometimes called local cloud collapse. In this model, instead of countless high-speed collisions, regions of dust and ice in the protoplanetary disk can become dense enough that gravity causes them to clump and collapse relatively quickly. Small pieces still come together, but the process is smoother, with lower relative speeds. Objects grow not by being battered into shape, but by gently gathering nearby material. Arakoth's shape and surface support the second story. Its lobes look as though they formed separately within the same region of the nebula, then slowly spiraled toward each other and merged without much violence. There are no obvious global fractures from intense stress, no signs that two hard, fast-moving rocks slammed together and shattered. Instead, the snowman appears to be a record of a calm, low-speed union. Studies of its geology, internal structure, and rotation have strengthened this interpretation. The way its gravity and spin balance out, the smoothness of its terrain, and the apparent lack of disruptive impacts all point toward formation through gentle, local collapse, rather than through a long chain of high-energy collisions. In effect, Arakoth has become a kind of fossil of planetesimal birth, a preserved snapshot of how small bodies may have first taken shape in the early solar system. For the New Horizons team and planetary scientists around the world, this was a quiet but profound revelation. A debate that had lasted for decades suddenly gained a strong, concrete example in the soft outline of a distant, flattened snowman of ice. We found support for the idea that many of the building blocks of worlds may have formed by calmly collecting nearby material, not by enduring endless crashes. Seen that way, the Kuiper Belt is not just a ring of frozen debris. It is a museum of beginnings, holding objects like Arakoth that remember how it felt to be at the very start of everything, when planets were still only possibilities waiting to be assembled. Thanks to New Horizons, Pluto is no longer just a fuzzy dot at the edge of a diagram. It is a place we have visited, however briefly, a distant world that for a moment had a passing spacecraft as its guest. In 2015, after nearly a decade of travel, New Horizons swept through the Pluto system on a fast, carefully choreographed flyby. For a few precious hours, it turned its cameras and instruments toward the dwarf planet and its moons, capturing details that had been hidden to us for all of human history. Instead of a pale, blurry speck, Pluto suddenly became a globe with light and shadow, plains and mountains, colors and textures. New Horizons studied not only Pluto itself, but also its largest moon, Charon, and the smaller satellites, Nix, Hydra, Kerberos, and Styx. These little moons, once only faint points of light in telescope images, resolved into real worlds with their own shapes and surface markings. For the first time, the far edge of the Kuiper Belt had a face. Most people remember one image above all, the view of Pluto, with a bright, pale heart shape spread across one hemisphere. That region, officially named Tombaugh Regio after Clyde Tombaugh, Pluto's discoverer, looks almost like an affectionate symbol the planet is holding up to the camera. But beneath that simple outline lies complex geology. The western lobe of Pluto's heart, known as Sputnik Planitia, is not just a patch of lighter color. It is a vast glacier made mostly of nitrogen ice, stretching about 1,000 kilometers across and plunging up to around 4 kilometers deep. By all accounts, it is the largest known glacier in the solar system, a broad, frozen basin, slowly flowing and reshaping itself over time. Its surface is patterned with polygonal cells, like a quilt, believed to mark areas where the nitrogen ice is gently overturning in slow convection, warmer material rising and cooler material sinking. The eastern half of the heart is different. Its brightness seems to come from nitrogen ice that has drifted and settled there, carried as frost from Sputnik Planitia and deposited over the landscape. Together, the two lobes create that iconic heart shape, but they do not share the same exact story. One is a deep, actively flowing basin. The other is a highland, dusted with transported ice. Before New Horizons, Pluto was often imagined as a quiet, heavily cratered ball of frozen rock and ice, ancient, inert, and simple. The spacecraft's data changed that picture. It revealed towering mountains made of water ice as hard as rock at Pluto's low temperatures, smooth plains with few craters, suggesting relatively recent resurfacing, and hints of hazy, layered atmosphere reaching hundreds of kilometers above the ground. Pluto turned out to be more complex and dynamic than many had expected. The heart-shaped region, in particular, sparked questions about Pluto's interior. Some researchers suggested that the weight of the thick nitrogen ice in Sputnik Planitia could be balanced by a subsurface ocean of liquid water or slushy ice, a hidden layer that might help support and shape the basin from below. The idea that such a distant, cold world could harbor an internal ocean was both surprising and quietly exciting. More recently, another possibility has joined the conversation. A study led by astrophysicist Harry Ballantyne and colleagues proposed that the origin of Sputnik Planitia might lie in a gentle but massive impact long ago. In this scenario, a large object struck Pluto at a relatively low speed and at an oblique angle, not straight on, but skimming in from the side. You can imagine it by thinking of tossing a water balloon across a dry sidewalk the way you might skim a stone across a calm pond. Instead of bursting exactly where it lands, the balloon scrapes along and then pops, leaving an elongated splash on the ground. The shape of Sputnik Planitia, with its offset position and broad, smooth outline, may be the frozen echo of such a low-velocity, glancing impact, a colossal splat that carved a basin and left behind a scar big enough to be seen from billions of kilometers away. Whether Pluto's heart is mainly the work of an internal ocean, a giant impact, or some interplay of both, New Horizons gave us the clues to ask the question properly. What once was guesswork can now be tested against real topography, real compositions, and real patterns of ice and rock. Charon, Pluto's largest moon, has its own story written on its surface. In the images sent back by New Horizons, one striking feature stands out: a vast belt of cliffs and fractures circling much of the moon near its equator. This enormous tectonic band suggests that Charon, too, has changed over time. One leading idea is that Charon once held a subsurface ocean of water ice that later froze and expanded. As the interior grew in volume, the outer shell may have cracked and stretched, leaving great chasms and ridges as frozen testimony to a long-vanished sea. Together, Pluto and Charon show us that even in the deep cold of the Kuiper Belt, worlds can have rich, internal lives. Glaciers that flow, crusts that break and heave, perhaps oceans that once stirred in the dark beneath the ice. As for what comes next, New Horizons is still traveling outward, coasting along its path through the Kuiper Belt. It is expected to leave the main belt sometime around 2028 or 2029, although the exact timing depends on how you choose to define the region's edge. For now, the spacecraft continues to send back measurements of dust, particles, and the space environment, quietly turning the empty-looking space between objects into something more fully mapped. There is currently no confirmed second flyby target beyond Arakoth, but astronomers are still searching the sky for small, reachable Kuiper Belt objects that new horizons might be able to pass. If they find one in time, we could be treated to another close-up glimpse of a distant, icy body. Another little piece in the puzzle of how the outer solar system works. Meanwhile, other tools are joining in from afar. The James Webb Space Telescope, with its sensitive infrared instruments, can study the light from Kuiper Belt objects and tease out the fingerprints of the ices and minerals on their surfaces. Even without flying to them, we can begin to understand what they are made of, how their surfaces differ, and how long they have been sitting in the cold. Someday, perhaps far in the future, a new robotic mission might go beyond flybys and try something more ambitious, orbiting a Kuiper Belt object, landing on one, or even collecting a sample to bring back to Earth. A small handful of grains from such a world could be a time capsule from the very birth of the solar system, preserving subtle details of chemistry that are hard to read from a distance. For now, though, we make do with glances, one icy world at a time, slowly lighting up the Kuiper Belt with understanding. If you let your thoughts drift back inward toward the sun, the scene changes dramatically. Instead of frozen nitrogen plains and distant starlight, you find yourself near a star whose light is overwhelming, whose atmosphere stretches out in a hot, delicate halo, the corona. Orbiting there, in a vantage point between Earth and the Sun, is the Solar and Heliospheric Observatory, or SOHO. Launched in the mid-1990s, SOHO has spent more than 25 years watching the Sun's face and its surroundings. Its main job has been to study the solar wind, monitor the outbursts we call coronal mass ejections, and observe the structure of the Sun's outer atmosphere. In doing so, it has helped us understand space weather, how storms on the Sun can ripple outward and affect satellites, power grids, and the thin skin of Earth's atmosphere. But along the way, SOHO has also become an unexpected comet hunter by carefully blocking out the Sun's bright disk with an internal, artificial eclipse. SOHO's cameras can see the faint region around it. In these images, small things sometimes come into view, tiny, bright streaks moving rapidly toward the Sun, growing brighter and often vanishing from one frame to the next. Many of these are sun-grazing comets, icy bodies, whose paths carry them dangerously close to our star. Over its years of operation, SOHO has discovered more than 4,000 such comets, most of which were completely unknown until they blew through this inner region. They arrive from many directions, on highly elongated orbits. Some swing around the Sun and survive, leaving on new paths. Others are destroyed by the intense heat and tidal forces, disintegrating as they skim the corona. SOHO is not the only observatory to witness these fragile visitors. Spacecraft like Stereo and the Solar Dynamics Observatory, also designed primarily to watch the Sun's activity, have caught sight of sun-grazing comets as well. None of these missions were built with comet hunting as a main goal, yet all have contributed to a growing catalog of objects that would otherwise have slipped past us unnoticed. Sun-grazers are mostly long-period comets, with orbital periods measured in hundreds or thousands of years. Their orbits are extremely elliptical, bringing them from the deep outer solar system, or possibly even the Oort cloud, down to within a hair's breadth of the Sun's surface. As they fall inward, they accelerate under the Sun's strong gravity, trading distance for speed. By the time they reach perihelion, their closest point to the sun, some of these comets may be moving at around 0.2% of the speed of light. That is an almost unimaginable pace for an object the size of a house or a mountain. In the space of a single hour, a sun grazer at that speed can cover more distance than Earth's diameter. And yet, against the immense scale of the sun, they are tiny, delicate things, often torn apart by heat and tides in the very moment they put on their brightest show. From the frozen plains of Pluto to the roaring corona of the sun, comets weave through all of these environments. New horizons, far away in the Kuiper Belt, and solar observatories like SOHO, close in at the sun's doorstep, are simply two different angles from which we listen to the same long, quiet conversation between ice, light, and gravity. When you watch the tiny bright streak of a sun-grazing comet rush toward the sun in a coronagraph image, it can seem like a brief, isolated event, a single, icy wanderer making a final, reckless dive. But most of the sun grazers we see are not truly alone. They belong to a family. Astronomers have traced the orbits of thousands of these comets and found that many of them follow almost exactly the same path through space. This has led to a quiet but powerful conclusion. The majority of sun grazers likely come from one enormous parent comet that was torn apart a few hundred years ago. That original body, now long gone, seems to have fractured into many pieces, each one continuing along the same general orbit, like a string of pearls slowly spreading out. Over time, the fragments have drifted apart along their shared path, so that instead of one spectacular visitor every few centuries, we see a steady trickle. As some of the larger pieces approach the sun, they too can break up, spawning even more small comets. The family tree branches and rebranches, turning one ancient object into a river of icy shards. One of the brightest comets of the last 1,000 years, Comet Ikea-Seki, is thought to have been one of these fragments. When it approached the sun in 1965, it became so luminous that it could be seen in broad daylight near our star, an almost uncanny sight for those who looked up a near-sun companion sharing the sky with the source of all light. Another fragment from this same family lit up the skies of the southern hemisphere in 2011. This was Comet Lovejoy, a sun grazer that threaded its way through the sun's outer atmosphere, the corona. It was not as dazzling to the naked eye as Ikea-Seki, but it made for extraordinary long exposure images. Solar observing satellites watched it plunge into the glare, trailing a soft, glowing tail. By most expectations, Comet Lovejoy should not have survived. At perihelion, its closest point to the sun, it spent more than an hour immersed in coronal temperatures of around 1,000,000 degrees Celsius. That environment is harsh beyond anything we can easily picture. Fierce radiation, intense heat, and powerful tidal forces all acting together. Yet, to the surprise of many, Lovejoy reappeared on the far side of the sun, still largely intact, though undoubtedly scarred and stripped by its near-death passage. It fizzed away, its brightness diminished, but its survival at all felt like a small miracle. The story was different for another famous sun grazer, Comet Ison. Before its close approach in 2013, many people hoped it would become a brilliant object in Earth's sky, perhaps even visible in daylight, like some great comets of the past. As it rushed inward, instruments trained on the sun watched Ison brighten beautifully. The comet's approach was promising, a graceful arc falling toward the star. But as it reached perihelion and passed behind the sun's disk from our perspective, something changed. On the other side, Ison emerged, faint and ragged, and then its light faded away. Whether the nucleus survived as a small, inert shard or was completely destroyed, we still cannot say with certainty. What seems likely is that, if anything solid remained, it no longer held significant ices. The volatile materials that give comets their come and tails were probably boiled off. All that was left, if anything, was dust and fragments, too modest to become a noticeable comet again. Even these comets Lovejoy and Ison, Ikea Secchi and their kin, are among the larger sungrazers we've observed in recent years. Their nuclei may have been a few hundred meters across, perhaps more. Many others are far smaller, only tens of meters in size, more like big boulders than mountains. These tiny comets often go unnoticed until they suddenly streak into the field of view of a solar observatory, brightening rapidly as they race toward the Sunday. For some of them, their entire known life in our records lasts only minutes or hours. They appear, they dive, and they are gone. Sungrazers can take different paths around the sun from our line of sight. Sometimes, a comet passes behind the solar disk, hidden from us at the very moment of closest approach. If it is completely destroyed, it simply never reappears. We infer its fate from its absence. At other times, the geometry is kinder. The comet skims past just above or below the sun's visible edge, and we can watch as it brightens, sheds mass, and, in some cases, visibly disintegrates in the glare. Close to the sun, the conditions are unforgiving. The heat is so intense that ices vaporize almost instantly. Dust and rock grains are blasted away. Gravitational tides, differences in the sun's pull between the near side and the far side of the comet, can stretch and stress the nucleus. Our own close-up missions to comets, like Rosetta's visit to Comet 67P, suggest that many comet nuclei are not solid, monolithic chunks, but fragile, porous piles of rubble held together only by their own weak gravity. Combine that delicacy with the sun's overwhelming influence, and you have objects that are easily broken, reshaped, or destroyed. Even the largest sungrazers rarely escape without heavy damage. Some split into multiple smaller pieces. Others lose so much mass that they become only pale ghosts of their former selves, fading into faint dust trails that slowly disperse. There is another curious pattern that has caught astronomers' attention. In some coronagraph movies, you can see a sun-grazing comet rush in, and at almost the same moment, a coronal mass ejection, a CME, bursts outward from the sun, sending a billowing cloud of plasma into space. The timing looks uncanny, as if the comet had somehow poked the sun and triggered the eruption. There are many examples of this kind of near coincidence, yet when scientists investigate more deeply, they keep returning to the same conclusion. The comets are almost certainly not causing the CMEs. The sun's eruptions involve energies and scales far beyond anything a small, icy nucleus can influence. The magnetic fields and plasma structures that lead to a CME build up over hours or days. A comet only spends a brief time in the corona, and its mass is minuscule compared to the sun's. So the current view is that these alignments are just that, alignments. Two dramatic things are happening in the same place at roughly the same time, but for different reasons. To our pattern-loving minds, it is hard not to feel that one must be causing the other. The physics, though, suggests that the sun would have erupted anyway, with or without the passing of a comet. Even if sun grazers are not stirring the sun, they remain deeply useful to us. We cannot send a spacecraft directly into the deep corona. The heat and radiation would overwhelm our technology, but comets do it for us, over and over again, as part of their natural orbits. They are, in a way, unintentional probes, throwing themselves into a region we can only watch from afar. As a sun grazer dives in, its tail responds to the environment it passes through. Far from the sun, a comet's tail is made mostly of dust and neutral gas, pushed gently backward by sunlight and the solar wind. Close in, the particles in the tail are heated and ionized. They become plasma, a charged gas that interacts strongly with magnetic fields. Viewed through ultraviolet and other specialized cameras, these plasma tails are clearly visible. Sometimes they wiggle or kink, shifting shape as the comet moves along. Those ripples are not just random motions. They are thought to be the visible traces of how the tail is responding to the sun's magnetic field lines in the corona, bending and twisting along with them. By studying those subtle movements, scientists can infer details about the magnetic structure and density of the corona that would otherwise be hidden. Each sun grazer becomes a kind of tracer particle in a giant, invisible flow. The more such comets we observe, the better we can map the patterns they reveal. Space weather, the storms and changes in the solar wind and magnetic field that can affect our planet is still something we do not fully understand. We know that CMEs and flares can disturb Earth's magnetosphere, trigger auroras, and sometimes disrupt satellites or power systems. We are learning to forecast these events, but our models are far from perfect. Information from sun grazers, moving through the regions where CMEs are born and shaped, adds one more piece to that complex puzzle. So, in the quiet interplay between ice and fire, we keep learning. A long ago giant comet shattered into a family of small sun grazers. Those pieces now rush in toward the sun on orbits that last centuries or millennia, some dying quickly, some lingering a little longer. Each one, as it falls, tells us a tiny bit more about what waits near our star, about magnetic fields and plasma, about heat and tides, about how a small, fragile body behaves when it strays too close to a powerful source of light. If you close your eyes for a moment, you can imagine one of these comets far above you now, still distant, still cold, slowly making its way along a stretched out path that will one day carry it into the inner solar system. When it finally arrives, instruments will turn to watch, and for a brief time, it will sketch bright, delicate lines into the sun's outer atmosphere before melting away. And somewhere here, under a much gentler sky, you are simply breathing, listening, and letting those distant motions drift through your thoughts like a soft, passing glow.